Hi students, welcome on the channel. So in this lecture we are going to talk about the solenoid, why the magnetic field outside the solenoid is zero. So first of all, how does solenoid practically looks like? So here you can see this example of the solenoid, where this kind of arrangement, we call it as the solenoid, where what we do is basically we take a kind of cylinder like this, okay, and then on that top of that we'll do the winding of some wire like that. We'll wind the wire on that. Of course it will be closely winded, okay, like you can see in the picture, and these wires which we take will be coated with a insulating surface, so that like if they are closely winded like this, so there will not be any transmission of the current due to the uh, physical interaction between them. The current will just flow through the wires like this, correct? So the question is like when we deal with the solenoids in this our chapter electromagnetic induction, we take that the magnetic field outside the solenoid is zero. Now why it is zero? So let's take some diagrams to understand. These diagrams I have taken from Concepts of Physics S.C. Verma, so you may also find the explanation there. So I am just explaining a bit more in detail. So here, like if I take this one of the ring kind of like this, and let's suppose the wire is the current is flowing like this. So if I use the right hand thumb rule, then the magnetic field lines of course would be like this, passing through it, as they have drawn these thick lines like that. So magnetic field lines will be like that, okay. And what if I take the another ring like this, in which the current is flowing like this nearby? So then this will also act like a normal magnet, where the magnetic field lines will go outside like this and will come back like this. So just to understand what will happen if we place both of these current carrying rings nearby each other, so what will the interaction of magnetic field? Let's take 2 points. Like for example, if I take a point here and here, they have named them as P and Q. So if I take P point, so look at the P point. For the loop 1, the magnetic field lines will be in upward direction, right? For the loop 2, the magnetic field will be in the downward direction. So will they try to cancel out? Yes. At P point, the magnetic field lines will be opposite. So let's suppose if we write down the magnetic field intensity at that point, so then you will say B1 vector plus B2 vector, and they are in opposite direction. So that's why you will say B1 minus B2. And if you place them nearby, of course these b1 and b2 will be equal, so this will come out to be zero almost, because of course the direction may be little bit in different direction. So that's why we'll not completely get it zero if we just have two loops like that, okay. So now something like this will have the magnetic field. Why the magnetic field inside is not getting cancelled out? Because look at the inside. If I take an inside point, so this is one loop, okay, this is our one loop, okay, and the magnetic field inside is, okay, complete magnetic field is something like that, okay. It is a like not exactly like this, but it will be something roughly like this, okay. Now if I take the another loop nearby like this, keep in mind we are just taking two loops and we are trying to understand this, so that if we have multiple loops, so then we can get some understanding of with the help of the two loops. So for the second loop, it will look like this, okay. The magnetic field will be like this, and of course the current is same direction, because why we are taking the same direction? Because the current will flow of course in same direction, okay. So try to think it like it is a clockwise current, okay. Okay, let me I think I have marked a bit different, so something like this, okay. These are two loops. If you look it differently, so then it may be like okay, different kind of picture, but if you look from this side, I am taking the clockwise direction of current, so then the magnetic field, of course I have drawn it like this, both magnetic field will be like that, okay. So here I was saying that it will cancel out, but if you look at inside point, here the magnetic field is like this, and for this also magnetic field is like this. If they are very close, then let's suppose that point is Q, inside point is Q. So at Q point, we'll say magnetic field is b1 vector plus b2 vector, and both will be parallel and in forward direction or in the right hand side like this. So can we say that it will be b1 plus b2, right? Okay, so that's why what happens if we place two loops closely, or even like if there is a distance in between them, magnetic field insides will be kind of added, and if we go to the outside, some part of that magnetic field will cancel out. Now what we do is, let's suppose now we have multiple loops, because what we are doing is we are doing the winding like this, okay, because we want to create a solenoid. We just do not want to have two loops, because two loops are not going to create a solenoid. So that's why we have a winding like this. In this winding, we can also consider again the same kind of phenomena where the multiple loops are there, right? So if multiple loops are there, then these, if I have three loops, so then for the three loops like this, the magnetic field inside will be again, it will be added, and the resultant will be in the right hand side, and the outside magnetic field will cancel out. Now what about the far point here? Of course there will be some component of magnetic field which will be getting like this. But the problem is that if we treat it as a wire as well, then some part of this magnetic field or this wire magnetic field will cancel out even these magnetic field. So what happens if we closely wind a winding? So then something like this will have the wires. With it taking the approximations are that the length of the solenoid is very long compared to the whatever this dimension is. Let's suppose if it is a rectangular solenoid, so then it will be something length of the rectangle, or otherwise if it is a circular solenoid, so it will be the diameter of this. So that is far lesser than the length, whatever that is. So because of that, these magnetic field lines inside become almost parallel, although for the two it will not be like that. For the two it will be more kind of unsymmetric. But if we take the multiple close windings like that, so then the magnetic field will become parallel, and outside it will be almost diminished. It will become zero because the magnetic field lines are cancelling out each other. So in total, if we take this solenoid, it will behave like a bar magnet, okay, but because the ends of the bar magnet are very far to each other, so that's why in between the magnetic field outside points will be almost zero. And that is why we can say that the magnetic field because of the solenoid at the outside point is zero. I hope you understood this. We can even prove it mathematically, that why the magnetic field outside is zero. The mathematical explanation generally I give is like this. Let's see, like we have this diagram. I'm just explaining with the help of this diagram. So what I do is, let's take it like this, a loop like this. I'm taking a Ampere's loop, correct? A loop which is passing like this from the outside of the solenoid. The both ends are like this. I am taking a rectangular loop like that, okay? Then I will say, according to our Ampere's law, we will have integration of BDL is equals to mu naught sigma I. Sigma is the total current. Now you take a loop like this, then let's suppose these number are something like 10 number of the magnetic currents which are coming out. Then do we have the 10 number of the wires for which the magnetic field will be going outside, right, or otherwise inside, just opposite of that, okay? So if we apply this formula, Ampere's loop law, the sigma I, the total current becomes 0, okay? So total current becomes 0, then you will have integration of BDL, it must be 0. What it implies is that BDL integration must be 0. So if I break it into the parts, so then I will say, okay, because this loop has these parts, so let's name it like this, 1 2 3 4. So then the integration of the BDL for 1, where integration of BDL for 2 plus integration of BDL for 3 plus integration of BDL 4 is equals to 0. We can say like that. Now see, for this one, of course BDL, for this one let me mark it, For this one, the BDL integration must be 0 because the magnetic field is like this and this is like this, so angle is 90 degrees. So for the second and fourth, the integration of BDL anyway is 0. Okay, it doesn't matter whether the magnetic field is 0 or not. So this becomes 0 and this becomes 0. Now remaining are two parts. So now it says, this same equation says that, okay, if you take this, so that integration of BDL vector for the 1 plus integration of BDL vector for the 4 must be 0. Okay, now 1 can be only 0 because magnetic field is like this. Here it will be something like this or just opposite of that maybe. Okay, and here also it will be like this. So first of all, integration of the B vector dot DL vector will be something positive value, and then the if the magnetic field is 0 here, then only this integration is coming out to be 0. So that's why it is going to be 0. This is how we can also explain this, but the better explanation is just we can understand it like this graphically with the help of the magnetic field lines. Okay, so I hope you have understood this part. Thank you very much. If you have any other doubts, you can ask on the comment section, and if you want me to make any other video on any other topic, let me know. Thank you.